Lagrangian interpolation is a method of finding a polynomial which kind of fits your data. So let's take a look at what the typical setup is. So let's suppose that you have a bunch of observations. So you have, let's have a two-dimensional case with x and y coordinates. Let's suppose you have measurements for x being equal to 1, let's say 2, 3, and then 5. And you have some values corresponding to these measurements. So the idea here is that you want to construct some polynomial in order to approximate this set of data. And essentially what you want to do is, for example, you want to find out what is the value of y when x is equal to 4, for example. So how do you do that? Well, one of the ways this can be done is with polynomials, and essentially what happens is that you're attempting to have an approximation such as, well, a simple polynomial would be a line, just a linear kind of approach, or something more complicated like, let's say, a parabola going like this, or maybe you know, a hyperbola going like this, or something else to that effect. So the idea is, how do we find the actual formula for all these polynomials? And for a number of points given let's say n plus 1 points, what we can do is we can try and formulate the interpolating polynomial in the so-called Lagrange form. So essentially what we're saying is we're saying that f of xi is equal to the sum from I going from 0 to n of y at this location times li, where li is that polynomial. And we'll see what it is in a second, because I'm going to rewrite it as the sum from I equals 0 to n of yi, and the polynomial itself is a product of the following. So it's a product of x minus xj divided by xi minus xj, where I is not equal to j, like so. So this may seem a bit cryptic, but we can now write out the polynomials for, let's say, 2 points. So let's say you have 2 points, x0 and y0, and x1, y1. What you can do is you can formulate this for 2 points, and it would look like this. So you would have f of x being equal to x minus x1 divided by x0 minus x1 y0 plus x minus x0 divided by x1 minus x0 y1. So the idea here is that if you have, let's draw the graph again. So if you have 2 points, so you have a point x comma y here, then the interpolating polynomial is just a line going through these 2 points. So it's going through x0, y0, and x1, y1 here. x1, y1, like so. Now for 3 points it gets a bit more complicated, because we now have x0, y0, we have x1, y1, we have x2, y2, so there's going to be more terms in the addition. So essentially for this, the function of x is going to be x minus x1 divided by x minus x2 divided, that was a multiplication rather, than divided by x0 minus x1, x0 minus x2, y0, and then there's going to be another 2 terms, because then what happens is we have x minus x0 multiplied by x minus x2 divided by x1 minus x0, x1 minus x2, y1 plus, and then the third term. So the third term is x minus x0 x minus x1, sorry, that should be a 0 here, 0 divided by x2 minus x0 multiplied by x2 minus x1, all multiplied by y2. So if we now draw the picture for this setup, we'll have something like the following. So essentially we have the point, this point xy, which lies on a line going through these 3 points. So essentially we have some sort of parabolic curve going like this, and then we know that this point is x2, y2, and some point here is x1, y1, and this will be x0, y0. Okay, so there is a general formula that you can use for interpolating this, for getting this set up, and it looks a bit convoluted. So let's try to write this out anyway. We essentially have a function represented as a large product, so that would be x minus x1 times x minus x2 all the way up to x minus xn divided by, and here we have x0 minus x1, x0 minus x2, and all the way up to x0 minus xn multiplied by y0 plus, and then you get the similar kind of thing for y1. So let me just write this out. So we have here x minus x0, so x minus x2 all the way up to x minus xn divided by x1 minus x0, x1 minus x2, and once again all the way up to x1 minus xn, y1 plus, and then there are lots of terms here, and essentially you get somewhere towards the end, and towards the end you get something like the following, and this is going to be a bit long, I admit, but essentially you get something like x minus x0 times x minus x1 all the way up to x minus xi minus 1. So getting close to the end of the whole thing, times x minus xi plus 1, and then all the way up to x minus xn. And this is all divided, should learn to draw straight lines, this is all divided by xi minus x0, xi minus x1, and then here we have xi minus xi minus 1, so 1 multiplied by xi minus xi plus 1. Oh, that should be a 1 again. Let me just edit it for clarity. So that's a 1, and multiplied all the way up to xi minus xn and times yi, and then the final term in this addition would be x minus x0 times x minus x1 all the way up to x minus x n minus 1 divided by x n minus x0 xn minus x1 all the way up to xn minus xn minus 1 times yn. So this rather convoluted formula is how you would go about taking a few values that you already have observed and actually getting a formula for them. So let's do a practical example of how you would do something like that. So let's suppose that we have a set of x and y values. So I'm gonna just draw a simple listing. So I have x values of 0, 2, and 5, for example, and I'm going to have the y values of 1, 10, and 4. And what I want to do, for example, is I want to calculate the value of y given that x is equal to 10. So what is it? Now we're going to apply this formula up above, so let's do that. So essentially our function is going to be something like this. So we take these values and we plug them into the numerators and denominators. So we're going to have 10 minus 2 times 10 minus 5 divided by 0 minus 2, 0 minus 5, multiplied by the first y value, so that's a 1 times 1, then plus, and we have 10 minus 0 times 10 minus 5 divided by 2 minus 0, 2 minus 5, multiplied by the second y value, which is 10, and then the third term is 10 minus 0, 10 minus 2, divided by 5 minus 0, 5 minus 2, multiplied by the last value, which is 4, and what we end up with is 4 minus 83.33 plus 21.33, which is equal to minus 58. So there we have it, without getting the actual polynomial written out. We already got our value, because essentially we took the 10 from here and we plugged it into the equation down below, and so we got our result. And now that we've looked at how this is done manually, let's actually jump into MATLAB and see how it's done there. Here is the implementation of Lagrangian interpolation in MATLAB. What you can see is that we're performing the summation of the different terms after each term is expressed as a product. So we essentially have the Li at each step being subsequently multiplied by each of the fractions. So effectively you can think of long fractions that we've written previously as fragmented into these separate xi minus xj over xi minus xj fractions, and then we keep multiplying them, excluding the condition when j is equal to I, and subsequently we perform a summation of all of these terms. So as a result, what we can do is we can take the data that we've just seen, plug it into this implementation, and see if we get the same result. So if you remember, we had x having the values 0, 2, and 5, and we had y with the values 1, 10, and 4. And we wanted to find out the value of y at x equals to 10. So let's do that. Lagrangian interpolation, provided the x, the y, and the value we're solving for. And as you can see, the result is minus 58, which is exactly what we had when we did it by hand.